from Nice, who will talk. Perfect. Who will talk about geometric generalized Wronskians and their applications to foliations and hyperbolicity. Please, Antoine.
Okay, first, I would like to thank the organizer for the invitation. It's for me a great pleasure and honor to give a talk at this seminar. And so indeed, I will talk about generalized Wronskian and applications. So first, let me set up a few notation. So we fix P an integer, so it's going to be fixed actually for the whole talk. And we consider U a word written with the alphabet 1, 2 until P. And we consider two words to be the same if we can pass from one word to the other by a suitable permutation of the letters. So accordingly, any word can be uniquely written in this fashion. And we will denote LU, the length of the word. So to any such word, we can associate the partial differential operator, du, which is simply you differentiate according to the direction defined by the word u. And so this acts on the sheaf of holomorphic function in a p variable. So that being said, we can now define generalized Wronskian. So this definition goes back to Wronski for p equal to 1 and Ostrowski for p strictly greater than 1. So we take U, a set of words, U1, U2, UM, and we will say that U is admissible if and only if the following condition is satisfied. So we require that the length of UK is less or equal than K for every K between 1 and M. So of course, for this to make sense, we have to adopt a way to order the word inside in U. And so we will start by ordering the word of length 1 according to the lexicographic order in N, then the word of length 2 according to the lexicographic order in 2, and so forth. And so we can then check this condition. So to any admissible set U, we can associate the following operator. So we take M plus 1 holomorphic function in P variable, and with them, we form the following matrix, where on the first line, we put the function. On the second line, we put the function that we differentiate according to the first word, and so forth, until we exhausted the words in the set BU. So we obtain a square matrix, and we take the determinant. And so such an operator will be called a pure generalized Wronskian of size M. So once this is defined, we can consider the vector space spanned by all these pure generalized Wronskian that we will denote in the following fashion. And we consider every linear combination possible of this pure generalized Wronskian associated to an indivisible set. And so an element in this set is then called a generalized Wronskian of size M. So for example, for p equal to 1, there is only one admissible set of size M. So you have to take 1 square until 1 to the power M, and it's the usual Wronskian one can encounter in one variable. And if you take p equal to 2 and m equal to 2, we can list the set of admissible sets. And so here there are 7 of them. So the fundamental property of Wronskian and generalized Wronskian is that they allow to read linear independence of holomorphic function. Namely, if we take m plus 1 holomorphic function in p variable, then they are linearly independent over C, if and only if there exists a generalized Wronskian, which, when evaluated on this function, does not give something identically 0. So usually, this theorem is stated with the pure ones, which actually is the same, as this is the span of the pure ones. That being said, so this is for the usual background on the generalized Wronskian. We will now introduce what we call geometric generalized Wronskian, and it's simply defined in the following fashion. So you consider the subvector space defined in the following fashion. So you take the the generalized Wronskian that satisfy the following homogeneity property. So if you take m plus 1 function, you multiply all of them by the same function, you evaluate a function on it, you ask that this function comes out, and the only possible power actually is m plus 1. So first natural question is to find among the pure generalized Wronskian the ones that are geometric. So this is not too complicated. So we will start with a definition. We will say that the set of words U is called full if and only if the following condition is satisfied. So we ask that for every word in the set U, so every word U, all the subwords of U remain in the set. And so in this case, one can check that the pure generalized Wronskian associated to it is geometric. And so we'll call it accordingly a pure geometric generalized Wronskian. So for example, for p equal to 1, there is no difference between geometric Wronskian and Wronskian. It's easily checked that this homogeneity property is satisfied. And for p equal to 2, m equal to 2, the full sets that are possible are these ones. So I will quickly go back, but for instance, here this is not a full set because the word 2 does not belong to it. Okay, so now we have found among the pure ones the ones that are geometric, but there are actually many more. And there is a way to find some other geometric Wronskians that are not pure in the following fashion. So we consider the group of biolomorphism of CP0, and we let it act on the vector space of geometric generalized Wronskian as follows. So we take psi biolomorphism of CP0, W generalized Wronskian, and we let psi act on W simply by reparametrization on the source of the function. So here it has to be understood in the following fashion. So we consider the function and their derivatives as formal variable. And here we have a linear combination of big determinants, and we can apply the formula to compute partial derivative of composition of function, then develop the determinant by...
I have a question. Could you please explain by holomorphisms?
So this is just here defined around 0, and you ask that it's holomorphic and it has an inverse that is holomorphic. So it's a map from a small neighborhood of CP to a small neighborhood of CP, and that is holomorphic and has an inverse that is biholomorphic. And so basically you just have to ask that the differential of the map on 0 is invertible. So you can develop it into a series in several variables. And you just have it to be that the linear part of this series is invertible. And so it will be then a biholomorphism. So you have, of course, to have the convergence around 0, but this is what we mean by that.
Thank you.
And so, as I said here, so you will develop it by multilinearity, and you will find a new linear combination of pure generalized Wronskian whose coefficients are going to depend on the partial derivative of the coordinate of this biholomorphism. So we'll do it. I will just give an example. It will be maybe more clear because it's quite abstract right now. So if we take p equal 2, m equal 2, and we take this pure geometric Wronskian. So we take a biholomorphism, we let it act on it, and what we find is the following expression. So we just have to do the calculation. So we have a polynomial in the partial derivative of the biholomorphism, and the coefficients of this polynomial are Wronskians. So here we recover, for instance, here, and here the pure ones, but we have some other ones here that are linear, that are combinations, linear combinations of generalized Wronskian, and actually they are geometric. And so, for instance, for this case, p equal to m equal 2, we have 3 pure ones and 2 other ones. So actually we can show that the space of geometric generalized Wronskian is of dimension 5 in this very particular case. And so a conjecture that I'm actually working on it actually at the moment is, I guess the following is true, is that for any integer p and any m, the vector space spanned by the coefficient of this. So actually we do exactly the same thing, but in greater generality, and we have something much bigger. And then it should be equal to the vector space of geometric generalized Wronskian. So that's something I checked in some cases, and I have some other reason coming from representation theory that maybe it should be true. Maybe it's not, but I'm guessing it for the moment that it's true. Okay, so far we have defined geometric generalized Wronskian, find the pure ones, and seen a way of how produce other ones by letting the group of holomorphism of CP0 act on it. But the fundamental fact is that the fundamental property of generalized Wronskian remains actually valid for the geometric ones. And so we have the following result. If we take m+1 holomorphic function p variable, then they are linearly independent over C, if and only if. So a weak form of the statement would be that we require that there exists a geometric generalized Wronskian on which when evaluated the function is not identically 0. And the strong form is that actually we can just check this condition on the pure ones, the pure geometric generalized Wronskian. And so this will allow us to obtain application. So now I will talk about them. So first in hyperbolicity. And so the goal of this part, this first application, is to prove the following results. So we take F inside the projective space of dimension n, a non-degenerate Fermat hypersurface of degree delta. So what does it mean to be non-degenerate? So in full generality, a Fermat hypersurface is an hypersurface defined by an equation of the following form, where here we allow coefficient before the power of the homogeneous coordinates. And require that it is not degenerate means that we want all the coefficients to be non-zero. So we can then take them to be equal to 1 if we want. So then we take a non-degenerate holomorphic map from CP to the Fermat hypersurface. So sometimes we'll refer to it as a family of entire curve. We will understand why in the next slide. And here, P ranges from 1 to n-1. And non-degenerate means here that the differential of the map is injective at least 1 point. Then if the degree of the Fermat hypersurface, delta, is strictly greater than n+1 times n-p, then the image of this map lies in a degenerate Fermat hypersurface of degree delta. So for instance, by degenerate, here we mean that there is at least one coordinate that does not appear in the equation. So for instance, we can say that it's included in this Fermat hypersurface, certain coefficients. So remarks, this result is known for p equal to 1, means it is due to Green and it uses Nevanlinna theory. And the result is also known for p equal n-1, and it follows from a result of Kobayashi and Ochai. But here, essentially, for these extremal cases, it does not use the fact that we have a Fermat hypersurface. It's a general theoretic statement. Whereas for p equal to 1, it really uses it. Okay, so first I will, to put the context of this result and be able to give a sketch of proof, I will first give a short introduction in hyperbolicity. So we take X a projective manifold, and by an entire curve, we mean a non-constant holomorphic map from the complex plane to X. And when we talk about hyperbolicity, at least for this talk, we mean that we want to study the geometry of entire curve inside X. So what do we mean exactly by that? So let's give an example. So let's take a simple projective variety, so a smooth projective curve. In other words, the Riemann surface. So if the genus of the curve is 0 or 1, then in this case, C is either P1 or an elliptic curve, and in both cases, C is covered by entire curve. So there are many of them. Whereas, as soon as the genus is greater or equal than 2, there does not exist any entire curve inside C. So why is that so? It can be easily seen. If we take a holomorphic map from the complex plane to C, by Riemann's uniformization theorem, C can be uniformized by the disk. So we can lift this holomorphic map to the disk, which gives an entire function that remains bounded. And by Liouville theorem, it must be a constant. So this is for the case of curves. And in a greater generality, there are conjectures that predict what to expect with respect to the geometry of entire curve inside the projective manifold. So here we will just discuss a particular case of a conjecture of Green, Griffiths, and Lang. So we will take X inside the projective space of dimension n, a smooth hypersurface of degree d. So it's given by the zero locus of an homogeneous polynomial of degree d with a certain condition so that it's smooth. And the conjecture says that if the degree is strictly greater than n+1, then there should exist a proper closed algebraic subset in X, which contains the image of every entire curve in X. So it's really a very strong conjecture, which is far from being proved at the moment. So what we know about it so far, so it was proved for general hypersurfaces in Pn of large enough degree. So here the degree is actually exponential in n, so we are very far from the optimal one. And what does it mean to be general? It means that if we fix a degree, we consider the parameters that define the hypersurface of that degree, and for a Zariski open subset of this set of parameters, the statement holds. And so this is due to De Verrier, Merker, and Rousseau. And actually, a bit later, a stronger result was proved by Brodbeck, saying that general hypersurface of high enough degree do not contain entire curves. So here we could have taken Z, the empty set. And in full generality, it is not even known if an entire curve cannot be Zariski dense. And the projective hypersurface is in this Pn, as soon, of course, as the degree is strictly greater than n+1. And so for people who know a little more about algebraic geometry, the real conjecture is that for a projective manifold of general type, there should exist a proper closed subset that contains the image of every entire curve, and being of general type means that the canonical bundle is big. Okay, so there is a general strategy to attack this conjecture, which is due to Green, Griffiths, Hsu, and De May in chronological order. And so, roughly speaking, the strategy is the following. The first step is to try to construct obstruction to the existence of entire curve or family of entire curve. And as we will see afterwards, this obstruction will consist of algebraic ODEs or PDEs that must be satisfied by such entire curve or family of entire curve. So this will be made precise right afterwards. And the second part is to find enough of them so that it forces the coordinate of the entire curve to satisfy an algebraic equation. Because with the step one, we know that we have relation between the coordinates and their derivatives, but we would like to deduce something only on the coordinate, as the conjecture tells us that it should hold, if we believe in it, at least. Okay, so to make precise this first step, we have to, we'll discuss a vanishing theorem, and we have to introduce some objects. So we'll fix X a complex manifold. Again, P is going to be a fixed integer. And for K an integer, we'll consider GPKX the fiber bundle of key jets of PGM from CP to X. So what is it? We'll describe the fiber over typical point. So we take X points in X. Then the fiber of this fiber bundle is the following. So we consider the holomorphic map, germ of holomorphic map from CP to X that pass through X. And we consider all their partial derivative up to the order K. And so the typical fiber of this fiber bundle is power of C, so it's a vector space. However, so of course, to write this, we have to pick coordinates on X. If we change coordinates, the structure of vector space will not be preserved by the chain of coordinates. So it's not a vector bundle, it's really a fiber bundle. And so we have a natural action of the group of biholomorphism of CP0 on it simply by reparametrization. So we reparametrize here. Now we'll define, so for D an integer, the vector bundle denoted EPKDX of PDEs of order K and degree D on PGM. So again, what it is, so we describe a typical fiber. So the fiber above a point of this vector bundle is simply made of the polynomial in the fiber of this fiber bundle over X, a polynomial in the partial derivative on pGerms. And we ask that this polynomial is homogeneous of degree D with respect to the action of C star on this fiber bundle, so C, which acts by reparametrization here. So for example, if we take P equal to 1 and K equal to 1, then G11X is simply the holomorphic tangent bundle. So we consider the germ of curve passing through a point, and we look simply at their derivative. For P equal to 1, K equal to 1, and any D, E11 dx is the D-symmetric power of the holomorphic tangent bundle. So say for D equal to 1, we recover the cotangent bundle. And I didn't say it, but here it's really a structure of vector bundle. So if one can check that if we change chart, so the formula is going to be quite complicated, but it will preserve the structure of vector bundle of the fiber. So now we can state the vanishing theorem, that will make precise what we said about obstruction to the existence of entire curve. So this is due for P equal to 1 to SU. And it goes as follows. So we take X a projective manifold, L an ample line bundle. So I will not define what it means to be ample, but here saying that the manifold is projective means that automatically you have such a line bundle, and fixing one means that you, in some way, fix a way to embed your abstract projective variety into projective space. And if we have a global section of this vector bundle, which vanishes along L for some KD, then the conclusion is that every holomorphic map from CP to X must satisfy the PDE that is defined by P. So what is the section? So here, just go back here. It's a map that goes from X and associated to each point in X, a polynomial here. And so it has to vary holomorphically in X. And so we see that really locally, we have a PDE in the, if we see it, if we see this as our entire family of entire curve, we really have a PDE. If we require it to be 0, we really have a PDE satisfied by it locally. So remark, so there is an equivalence between the fact that there exists global section. So here we took P equal to 1, but it's also valid for any P, for some KD, and the fact that X is of general type. And so one sense is due to, so this sense is due to component bound, and the other one is due to the main. So it makes really precise the fact that, well, on projective manifold of general type, there are obstructions to the existence of entire curve, or family of entire curve, made by the section of these vector bundles.
I have a question.
Yeah.
Could you please illustrate, if possible, each bullet in the theorem by a toy example?
So actually, we will see it in the proof. But this statement, actually, most of the time, it's really theoretic. So as I said, finding explicitly such a section is quite complicated. Even, I mean, we can do it in very few cases. And so, but we will see it in the sketch of proof.
And is it a challenge to find one? And is it an important challenge?
Yeah, actually, if one can find some, we can really work with it and see explicitly what obstruction it gives. And so this is very good to find them explicitly. But the problem is, we do not know how. We know, as I said, for theoretical reason that it exists, but no, we have barely no information actually on them. So in very particular cases, so for instance, for Fermat hypersurface, we can actually produce it, but otherwise, to my knowledge, no, it's a challenge.
So May I ask a question too? Just continue with Alex's. So without an example for X, L, and P, how do you know that the statement is actually correct other than from your proof?
Well, what do you mean? How did they come up with?
Yeah, I mean the proof is probably very complicated.
Actually, yeah. So okay.
I just want to, as Alexei said, I mean, you just want one example that satisfies your three conditions. Let's put it that way. So do you have an example where the hypothesis, I don't care the conclusion, that the hypothesis is actually satisfied?
Actually, no, it's complicated to construct such sections. So
so the three hypotheses could be inconsistent.
Oh no, as I said, we know that it's non-zero, but
okay. You got a proof of an existent theorem?
Yeah, so it's due to the Maillet, and actually it computes the Euler characteristic of this vector bundle. Okay. And so, well, it's quite complicated and very technical, but yeah, there is an existent proof. We know that if the manifold is of general type, this space for KD large enough is going to be this C vector space.
See, I mean, the conclusion is very, very unbelievable. I mean, that there is some differential equation that satisfies every holomorphic map.
But the thing is, it's
unless the equation is zero, right?
Yeah. So but as Antoine said, this is what happens, right?
P is non-zero. Well, actually, no. The D has to be greater than 1.
It is very restrictive to have such a map. I mean, it's not so. If there exists some.
You mean there are very few holomorphic maps from CP to X for any projective manifold?
Yeah, I mean, if you take, for instance, a general hypersurface, so it's a, I mean, so it was proved for I degree, but it's believed for, in Pn, if the degree is greater than 2n minus 1, it's believed that a general hypersurface is hyperbolic. So there are none, actually. Okay. So no, hyperbolic manifold actually do not contain any entire curve. And so the strategy is to...
So you're saying that the set of holomorphic maps from CP to X is very, very small and perhaps even finite or something like that? I mean, finitely generated, let's say.
Yeah, that's what it is the content actually of the conjecture. It says that if there exists some, it's really special. So it's really contained in something very small.
Ah, okay.
This is the content of the conjecture. Yeah. And so the idea is to find a lot of obstruction in here to say that, well, there cannot exist any, or if they exist, it's very miraculous in some way. That's the idea.
I have another question in connection to the statement.
Yeah.
So here you have a function depends on complex variables. So you're taking derivatives with respect to complex variables, correct?
Yeah.
And why not to take derivatives with respect to real and imaginary parts? Like, how different would this be?
Oh,
I mean, I do not know.
So, for example, if you get Cauchy-Riemann equations, right? So, so you'll open yourself to maybe more PDEs that the thing can satisfy. That's so I wondered. So when I was looking at it, I was trying to understand. Okay, so you do complex or you do real and imaginary. So you said you do complex.
No, we really stick in the we stay in the complex analytic setting.
Mm-hmm. So and how important is it to stick to that?
Well, I think it's believed that if there is a proof, it should somewhat stay in the realm of algebraic geometry. So here we just adopt the complex analytic point of view, but for projective manifold, it's actually the same. but well, I mean, we could define the thing is that if we change the definition of this and allow something more less restrictive, the space. I mean, the fact that we work in complex analytic settings says that, for instance, that the space is finite dimensional. If we start working with in the real setting, I mean, it should not give anything interesting. But I'm not sure I have really understood your question.
Well, my question is, allow P to have derivatives with respect to a real and imaginary part. What's then? Well, this will be, I guess, if that's true, then with the real imagined part, it will be even more true. But maybe I'm asking how useful this could be now. Is it interesting at all?
I haven't thought of that. That may be fruitful, but I really could not say.
Oh, thank you.
A silly question. You look at these Fermat surfaces. Is there any connection with Fermat's last theorem?
No.
Okay.
Not to my knowledge, but no, I do not think so.
Because the way you defined it is, the sum of the powers is equal to 0, if I remember right, or something like that. Yeah,
I mean, it is a Fermat hypersurface, but we thing is that they are really symmetric and nice enough so that we can do explicit computation, as we will see.
So there's no arithmetic component in the whole thing.
What?
There is no arithmetic component in the.
Oh yes. Okay, so but I'm not an expert in it. But yes, they are hyperbolicity. They are analog, arithmetic analog of hyperbolicity. Yes, but well, so for instance, you are not dealing with entire curve, but with rational points on the variety. But there is a dictionary. But I mean, I know it exists. I know a few cases, but this is not my area of expertise, so I could not. But there is definitely an arithmetic analog of that. Yes.
Okay. Thank you.
Okay, so now that we have set up the general idea of the first part of the strategy, we have to relate the construction of the Wronskians to this. So we have the following proposition. If we take X a projective manifold, L an ample-length bundle, and M+1 global section of this ample-length bundle, and we take Q a full set of size M, then the operator, the pure geometric Wronskian, will induce a global section of this vector bundle, so the order and the degree depends on U. And so see here that it's a positive twist and not negative. And so locally, it's defined on a trivializing of point set of the line bundle as follows. And so you take a PGM from CP to X that pass through X. You write the section in the trivialization chosen, and you compose it by your PGM. So you really have a map from CP to C. And so you can apply the definition of the Wronskian.
So, excuse me. So are you saying that this Wronskian on the S0 to SM is an example of P in the main theorem?
Yeah, it gives an example, but it's positively twisted. So it does not give something negatively twisted. Here it's positive. The key fact in the theorem is it's that it vanishes along L.
Okay, it's -1. All right.
Yeah, so this is the key fact. So we'll see how we can obtain something negative in the case of Fermat hypersurfaces.
Can I just ask for short clarification? So this action is it the same action defined before when by holomorphism we're acting on Wronskian, right? Or it's slightly different?
No, because here we have so no, it's not the same. It's a map from here to CP to XX.
Okay, yeah, thank you. Now I see. Okay, thank you.
And so just a quick recall. So okay, but if it was not clear, people would have asked. But the section is really a holomorphic map from X to L, and so and I will emphasize on that. So if we restrict the line bundle of two trivializing sets, so say on this trivializing set, the line bundle is simply U times C or U prime times C. And so we identify the two copies of C by a nowhere vanishing function. Yeah. And so if we change, because of course, this definition depends on the trivialization. And so to define something global, we have to understand how it goes when we change trivialization. And actually, when we change trivialization, we multiply each one of these sections by the same function. And so by the homogeneity property defining geometric Wronskian, it comes out. And actually, this is really the reason why we defined it in this way. And so this is why the L to the power m plus 1 appears here. Okay, so that being said, let us give a sketch of proof of the theorem at the beginning of the section. So we take F Fermat hypersurface of degree delta strictly greater than n plus 1 times n minus p. And we take a non-degenerate holomorphic map from CP to the Fermat hypersurface. So we will lift it to Cn plus 1 in the following fashion. And we will suppose, we can always do so, that F00 is not equal to 0 and that F is non-degenerate at 0. Then we will denote for U a full set. So here of size big N minus 1, so the same N than here. So we consider the following operator. So here I should recall that on Pn there is a tautological variant polynomial bundle O1. So the global section of O1 is simply the homogeneous polynomial of degree 1. And here we have homogeneous polynomial of degree delta. So it gives a global section of O2 delta. So this is why here we have this positive twist. And so we consider these operators for every full set. And the goal is to prove that PU de F is identically 0 for every full set of size n minus 1, because with the fundamental property of Wronskian, it will give us the existence of a linear combination of the n last coordinates of F that is going to be identically 0. So it will give us the equation of the degenerate Fermat hypersurface, degenerate here because the first coordinate will not appear. And so how do we do so? So first, we are going to distinguish two types of full sets. So first, we consider the full sets that do not contain a letter. So that as it is a full set, this letter will never appear in the group. So the fact that F is non-degenerate at 0 means that locally we can find a biholomorphism of CP0 such that we can write F circ phi locally in the following fashion. So up to doing a permutation of the coordinate, we can always write it in this fashion. So Z1 then P and GP plus 1 until Gn. And now we can just compute this locally. So we have this determinant. So here we have listed the word of U. And so note that we highlight here this column associated to ZE, so ZE to the power delta. And as E does not appear in all this word, when we differentiate, it's going to be always 0. So this is why we have this column. So here, why can we make appear this column? It's because we can use this equality since the image of the function lands on the Fermat hypersurface. We have this equality. And so by replacing this column by the sum of all the column, we obtain this. And so it has to be identically 0 as they are proportional. So this is the idea for the first case. And for the second cases, we consider so all the other full sets and observe that the order of the full sets has to be, so the order is the length of the maximal length of the word in the full set, has to be less or equal than n minus p, because you have to put at least 1, 2, and p, and then to obtain something with maximal order, and you have, of course, to keep a full set, you are obliged to do the following operation, so you can replace 1 by 2 or by 3 by p. So that being said, so remember that we picked really a particular global section. It was power of coordinates. So when we differentiate, actually, by multilinearity of the determinant, we can put that into factor. So and this works with, I mean, we are not obliged to work on a Fermat to do that. So actually, we have here a section which is, of course, still positively twisted, but less positively twisted. And the fact that we have this equality, as we are on a Fermat, by antilinearity of the determinant, we can add a further factorization. So this one. And this time, we get this twist. And so we get something negatively twisted with our hypothesis. And so we can use the vanishing theorem to conclude the proof of the result. And so, well, you see that this is really important to have some factorization trick to obtain something negatively twisted. And so it's very particular to Fermat hypersurfaces. Okay, so this was for the first application, so in hyperbolicity. And now we will give a second application, and we will use for this a very special Wronskian. So once again, P is a fixed natural number, and for n natural number, we consider this set. So what does it mean? It means that we put all the words written with the alphabet 1, 2, until P of length less or equal than m. So it is, of course, a full set, and we denote by m its cardinality. So since it's a full set, the Wronskian associated is geometric. So recall that it satisfies the following homogeneity property. And it also satisfies the following fundamental property, because, well, we picked it in a very particular way. If we let a biholomorphism of CP0 act on it, actually we recover it multiplied by a certain constant, which depend on the biholomorphism, and it's a determinant of the differential of the biholomorphism to a certain power that one can compute. Now let us see how to apply that to foliation. So first, I have to recall what is a foliation. So the easy cases. So in the regular case on the manifold, so we take X a projective manifold of dimension n, and we consider a foliation around P. So what does it mean? It means that we have a distribution of P planes, or another way to say that we have a subvector bundle of Px around P, namely that for every point in X, the fiber over X of the foliation is a subvector space of dimension P, and it has to vary holomorphically with X. So, well, to be a foliation, we have to add, of course, a condition, and we ask that it is locally integrable. So we say that it's an involutive distribution, and in practice, it means that around every point of X, we can find a neighborhood and trivialization, say, so it's a map of this kind to you, which is adapted to the foliation, which means that if we see this as, so if we fix W and we see this depending on Z, we differentiate it according to Z and see the image of the tangent plane of CP on Z, then we recover the fiber of our foliation. So that's what it means to be a foliation on a projective manifold. And so note that if we want to change trivialization, so of course trivialization adapted to the foliation, it's given by the data of a biholomorphism of this kind. So actually we have to somewhat reparameterize this and still satisfy this condition and for this to be true, this map has to be of the following form. So the first function depends only on W, and the second on W and Z. Okay, so this was a bit technical, but now let us see the idea why and how we can use Wronskian in this setting. So we will still fix an amperland bundle and take a global section of this amperland bundle. And the goal is to evaluate this Wronskian at a local integration of X around X. And so actually we can do so because this is a family, so parameterized by W, of germ of map locally from CP. So we can, if we pick a trivialization of our land bundle, write our sections in it, and evaluate as we did in hyperbolicity. This we can do that. We have a number. But of course, this depends both on the choice of trivialization of L and the choice of trivialization of the foliation here. And we have to understand how it changes when we change trivialization. So, well, with the property of this very specific Wronskian we chose, actually we know how it changes. So as it is geometric, here, if we change the chart, if we change trivialization for the line bundle, it will just be multiplied by this, as we already saw. And if we change chart for foliation, if it's the change of chart map, then it will be multiplied by this. And so this is because of the second fundamental property of this Wronskian that we described earlier. And so, well, all in all, this allows to create a global section of this line bundle. So here it's the line bundle L, and so, okay, we can take it for granted that the line bundle whose transition function on the covering are given by this define actually what we call the canonical bundle of a foliation, denoted in this fashion. And so we recover this alpha. With this construction, we can prove the following. So if we take X a projective manifold, F a regular foliation upon P, L an amperland bundle, and so we will denote by epsilon tilde what we could call the global tilde Césaric constant of L. So actually it's a measure of how positive the line bundle is. Then the line bundle, and so here we have adopted the additive notation, Kf plus P plus 1 divided by epsilon tilde L is numerically effective, which means that its intersection number with any curve is positive. So more concretely, if we take a curve in X and we restrict it to the curve, we can, what it means is that the degree of this line bundle, so it's a line bundle of a curve on a curve, plus P plus 1 divided by epsilon tilde the degree of this line bundle is greater or equal than 0. And the idea is to use the previous construction, but of course we have to ensure that we construct sections that first are not identically 0, and also that do not vanish at a given point to obtain the nefness. So here it's a bit more technical, but not too complicated either. And I think I'm maybe out of time. Don't know how many.
Yeah, I would say.
Okay.
But I guess, yeah, it represents the second application, right?
Yeah.
You also had the last one.
What?
But you have presented the second application, or you wanted to somehow elaborate on it?
No, I can present the second application if I have time, but it's.
Yeah, I think maybe it's better to we are a bit over time indeed. So let's maybe stop here for now. And first, thank the speaker. And please, questions. So let me just, I want to clarify a couple of things, because so you had 3 types of Wronskians, right? So you had like usual, like all Wronskians,
yeah,
geometric and pure geometric.
Yeah.
And pure geometric is a strict subset of geometric.
Yeah.
Right? But like in your first proof, you use pure geometric Wronskians.
Yeah, I use only pure, yeah, exactly.
And in the second, you use some, but
Actually,
in your,
for
but in
this,
your first,
only one, but for the last one, yeah, I use all of them.
Okay. But if just I want to get some intuition about the first application actually. So you used only pure Wronskians,
Yeah.
but you wanted to deduce linear dependence. But I thought that your theorem is that if all geometric Wronskians vanish, then you have linear dependence.
Yeah. So
right?
this is
Or it's
the
for
weak
pure.
form, but there is the strong form as well. So that's. Let me go back. So the weak form is that if there exists one, but
if in the leaf,
but the strong form is that we can actually only check it on the pure ones.
Okay.
Yeah.
Okay. I see now. I see. But then, what is the benefit of the weak form?
So the benefit of the weak form is actually the proof can be. What I did is that I proved the strong form, which of course proves the weak form, but with the, for instance, proof of Roth, it can actually be somewhat a bit changed to obtain the weak form with not too much. It's not too complicated actually to have the weak form from what people know from the general statement. So
it can be easier deduced.
Yeah. It can be really easy.
Okay. Thank you. Now I understand.
Sorry, could you clarify this statement here? The two bullets are equivalent to the hypothesis here. You know, there are three things that are equivalent. Is that correct? Or two things that are equivalent?
So yeah, actually they are all equivalent. Yeah.
So there are three equivalences, right?
Yeah.
Okay, because the way it is stated, it looks like that these two has to be together.
Oh no, it's so if they are linearly independent.
So there is an or. There's an or here or something.
What?
It's okay. All right.
So yeah, it's
three separate statements here.
It's two equivalences here, and so of course this one implies this one. So they are all equivalent. The strong implying the weak.
But the weak is enough to imply linear independence.
Yeah.
Okay. Yeah. So it's three things that are equivalent.
Yeah.
Okay.
Actually, this has to be.
One of them is trivial.
Yeah, when sense is trivial, of course.
But from here to from the strong to the weak is trivial. From the weak to the strong is not, of course.
Yeah, exactly.
All right.
Mm-hmm. Okay.
And so yes, the thing is that the set of pure geometric general Wronskian is not stable under the action of the biolomorphism of CP. And so as we see with foliation, we have to have something that is stable somehow. So that's why we consider the geometric ones. So I guess this is the smallest representation that contain, so the set of geometric as defined is, I think, the smallest representation that contain all the pure geometric ones. So that remains stable under the action of the biolomorphism of CP0.
Right. So the pure ones, they're not actually invariant in some sense.
No, they are not invariant.
So this is not that nice class. I see. Thank you.
So this is actually the idea behind this conjecture is that as soon as one has this Wronskian, if we let act the biolomorphism on CP0 on it, then we have to recover the whole space of geometric generalized.
Mm-hmm. I see.
Wow.
And basically, if the conjecture is true, then this would imply that the weak form implies the strong form.
Not exactly.
Not exactly, right? Oh.
No, actually, the difference between weak and form and strong has to be interpreted. So we can really make the analogy that we have an ideal and we want it to be either to define either set theoretically of sheaf of in a really scheme theoretically the ambient space, the underlying space. So the strong form says that set theoretically this is enough, but so it's like we have a subvariety defined by zero of polynomials, and so we can just be interested by finding the least number of polynomials that define the variety. But if we see it as a scheme, there is an ideal sheaf associated to it, and it's not clear that, and it's not always true, that the number of polynomial defining the zero also span the ideal. I don't know if it's clear.
Yeah, that makes sense. That's
so
yeah,
this is
that's
the difference
analogy.
between the two, actually. It has more to be understood in this way. So it's not really related to that.